So the problem says a pitot tube is connected to a manometer to measure the air velocity in a wind tunnel. If the specific gravity of the manometer fluid is 0.85, what is the airspeed? So you can see in the diagram that you've got a 20 millimeter deflection of the manometer, and you're told in the problem statement diagram that it's air at 25 degrees C and atmospheric pressure is 98 kilopascals, and we're after calculating the air velocity here. So we start with Bernoulli's equation, and we apply Bernoulli's equation between 2 points. That's how we will, in fact, that's how we'll always apply Bernoulli's equation. And so we're going to pick one point here, point 1, well upstream of the pitot tube, but on the sort of the center line of the nose of the pitot tube. And then point 2 is going to be right at the stagnation point, because a pitot tube uses the fact that the flow stagnates at the nose of the pitot tube, and that pressure rise is what causes the manometer deflection, which allows you to make the measurement. So now we write Bernoulli's equation at point 1 and point 2. And you can use any form you want. I'm going to use this one, P1 upon rho plus V1 squared upon 2 plus Z1 equals P2 upon rho plus V2 squared upon 2 plus Z1. So we have the pressure energy term, the kinetic energy term, and the elevation or potential energy term at each point. And the amount of energy in the flow remains constant at point 1 and point 2. Now we can see, of course, this is a manometer, so you can tell that gravity must be acting in this direction. So Z1 equals Z2. There's no significant change in the altitude of the fluid, the elevation, so we can cancel Z1. Oops, I should be at 2 there, and Z2. And as we discussed in some detail, a pitot tube works by the flow stagnating, coming to a complete stop at point 2. So all of the kinetic energy at point 1 is converted into pressure energy, and so V2 equals 0 because we have stagnation. So we can cross out that term. So now we can solve, this is quite a simple example, we can solve for V1, and it's going to equal 2 P2 minus P1 upon rho, and then all of that under this. The common mistake is to get the densities confused. When this density here is the density of air. It's the density of the fluid because it's where it came from Bernoulli's equation. And sometimes students get confused and they use the density of the manometer fluid. So we need to calculate the density of air, and I'm going to do that using the ideal gas equation of state. Now you could look it up in the table in the back of the book, but you notice the pressure is just slightly different than standard atmosphere being 101.3 kPa. So in the lab, you're probably going to measure the pressure using a local barometer, because the pressure varies from day to day, and you should really correct for that. So let's use the local atmospheric pressure. It's the more correct way to do it. So the pressure is 98 times 10 to the third newtons per meter squared. The gas constant for air, after a while you can go look it up, but you'll remember it is 207 joules, which is Newton meters per kilogram K, and the temperature here is 25 degrees C, but we've got to convert that 273 in order to put it into K. And now you'll notice that the units should work out. K goes with K, Newton goes with Newton, and you can see we have kilogram on the top and cubic meters on the bottom, which makes sense. So this works out to be 1.146 kilogram per cubic meter. It always amazes me that there's that much mass in 1 cubic meter of air. So that's the density of air. We now need to get P2 minus P1. And we're going to use the deflection of the manometer. And the pressure at 2 here, of course, is being felt on the right-hand side of the manometer, and the pressure at 1 is being felt on the left-hand side of the manometer. And remember from chapter 2 that in air has such a low density, we don't consider the pressure to change significantly with elevation. So the pressure on this side is P1 and the pressure on this side is P2. So let me just scroll to the next page and we'll calculate, we're going to calculate P2 minus P1 just using our manometer relations, which was the gamma of the manometer fluid times this height, which is 20 millimeters. Remember, that comes from, that's chapter 2. So let me just scroll to a new page so we can continue. Okay, so using our manometer theory, let me write this down. P2 minus P1 comes from the manometer. P2 minus P1 is then going to be the gamma of the manometer fluid times H. We're told that the specific gravity is 0.8, so the gamma of the manometer fluid is 0.8. Sorry, it's 0.85. 0.85 times the gamma of water times the deflection of the manometer. So that's going to equal 0.85. The specific weight of water is 9790 newtons per cubic meter, and then 0.020 meters. And that will give you the pressure difference between the stagnation pressure at P2 and the static pressure at P1. And that works out to, I got 166.4 pascals, or newtons per meter squared. So now we can make our substitution. Remember, we had that V1 equals 2 P2 minus P1 over the rho of air, square rooted. So we can take 2 times 166.4 newtons per meter squared over the density of air, which we calculated to be 1.146 kilograms per cubic meter. And you should always check, right? If we put in here that a newton is a kilogram meter per second squared, we should be able to check the units here. Kilograms go with kilograms, and that meter is going to make that a single meter, and then we cross that meter and that's going to make a squared. So we're going to have meters squared per second squared, and then when we take the square root, we're going to have meter per second. So it's always worth checking that out, taking just a moment to do that, and we get 17.0 meters per second. And that's the velocity of air